Hey everybody, welcome back to another round of physics, and yeah, let's get going. We are finished with our discussion about the electric and the magnetic field, and that whole discussion culminates with the idea that we can theoretically describe the nature of light using Faraday's law and the Maxwell correction to arrive at the conclusion that light propagates through space at a speed of c, related to both the permeability and the permittivity of free space. So now the remaining discussions will revolve around how we can focus light, how we can manipulate light, both through lenses and mirrors. So just to highlight for you the rest of the semester, we'll discuss both the law of reflection, which governs how mirrors work, and then we'll quickly derive Snell's law using Fermat's principle. After that, we'll discuss ray diagrams, how we can qualitatively assess a mirror, a lens, or a system thereof. And then finally, we can quantify objects and images using the lens maker equation. So that's kind of the rest of the term in a nutshell, and we'll go ahead and let's get some videos done. So the first off, thinking about mirrors, the rule of the game is fairly straightforward. First of all, when we're dealing with a mirror, we need to identify the normal. In other words, the line perpendicular to the surface of the mirror. Okay. After that, we have a simple idea that the angle of incidence is equal to the reflected angle. In other words, and please bear in mind, we measure everything with respect to the normal. So the angle of incidence would come in, and I would call it theta naught. Okay? What we say for a mirror is that the reflected angle is the same as the incident angle. Okay? And that's why I kind of started off the lecture with something like a surface of a CD. A CD or a DVD or a Blu-ray or any kind of disc is working off of the law of reflection. If you zoom in really carefully, say, with a microscope, I assume, is that you'll see that on a CD, there are pits on that mirrored surface. And each of those pits, for example, you can imagine light being on a smooth surface, and it will reflect off at a given angle, particularly if you have a reader to actually catch that reflected light. But then you can imagine that as the disk spins, maybe it hits one of these pits. So I better draw in a normal here just so I can get a reasonable reflected angle. And that angle will be different than where the location is for your reader. Okay? Bear in mind the relative position of the sensor is this far away. So for this piece, the sensor would be down here. And so the reflected wave will not be reflected to where the sensor is. Whereas conversely, later on, again, you get a reflection that does go to the sensor. And this is how DVDs, Blu-rays encode the information. Simply, when the light is received by the sensor, that might stand for a 1. When it is not reflected to the sensor, it stands for a 0. And that allows you to encode the binary data that represents the music, the soundtrack, the video, etc., etc. You might say, well, wait a minute, Greg, what's the difference between these? And simply, it is the matter of how tight, how closely packed can you get the lines of data. So a Blu-ray uses a blue laser, which can actually allow the information to be packed closer together without accidentally reading adjacent tracks. I mean, we always like to think of records as being so old-fashioned and DVDs and CDs being newfangled. But the reality is that they're working off of the same underlying concept. The information is encoded on little tracks. The only thing that differs is how it's read, whether it's a needle for a record or a laser for a CD, Blu-ray, etc. And that's pretty much it. Now, I should say that if we're thinking about manipulating light with a mirror, generally we have something like an angle. So I could say, well, go ahead, think about where's the reflected ray going to be directed for this particular situation. You go, yeah, I got it. So you go ahead and you draw in the normal, and again, you can visually see that the angle of incidence should be equal to the reflected angle. So if I do, I don't know what that would be, probably close to 45 degrees, I darn well better have 45 degrees on the other side. And so my reflected ray is going to be straight up, for example. Now that in itself is, particularly uninteresting. But the question would happen is, what happens if I have different angles for the triangle? So go ahead. You can think about which mirror in these three situations will have the largest deflection with respect to the incoming beam. And when I use the term deflection here, what I mean is angle between the incoming ray and the outgoing ray. So again, you can get a sense of, well, if I do the first one, I would have something like this. And so the reflected ray might be at 90 degrees. So, or excuse me, 45 with respect to normal, or 90 with respect to the incoming ray. Something like here, you can see that the angle, because the angle is larger, the reflection is going to be larger. And so right here, here's the deflection angle, which is, smaller. Similarly, a more steep triangle, again, we can get, there's our normal. And so the reflection should be something like this. And the deflection is greater than 90. Okay? So you get a sense of, as the angle of the mirror increases, you get a larger deflection. Okay? Now, how do we consider mirrors, like entire mirrors? These are, of course, planar, flat surfaces. But what happens if I have a curved surface? How do I approach that? And you already basically have the idea. If you understand these ideas about changing the direction of the triangle, changing the slope of the triangle, then you already know how you can think of, say, for example, a convex or a concave mirror. Imagine that I have 4 rays that are located at different spatial positions. This is nearest the bottom of the page. This one's a distance d above, et cetera, okay? And imagine that I would like to use a system of mirrors to get each of the reflections back to the same location in space. So for example, let's say that I'm aiming for this location in space. I want all of the reflected rays to pass through that spot. Good so far? Okay. So the first question is, if I'm thinking about, in fact, maybe I should number these rays. Let's go 1, 2, 3, and 4. Okay. So if I am thinking about ray 1, and the surface that it needs to reflect off of, do I need a large deflection or do I need a smaller deflection as compared to, say, something like ray 4? Yeah, good. You can see that the deflection for ray 4 has to be fairly large. Now you can see, okay, well, here's the path that ray 4 would follow. Here's the path that ray 1 would follow. And to get back to that location, the deflection here has to be rather large. This one, if I do it at the same location, maybe that's what I should have done, is not as extreme of an angle. Okay? That's the first thing. So the next question, if I were to use a flat mirror to redirect these rays, okay, which ray would need a steeper angled mirror? Yeah, good. And hopefully you see that 4 is going to require a steeper angled mirror, whereas one might not require as steep of an angled mirror. Okay? Smaller deflection, less angled the mirror. Larger the deflection, a larger angled mirror. Okay? And so now you can get a sense of, for example, not as steep, more steep, more steep, steepest, as I think about each of these rays. And indeed, you could say, well, okay, so you could think of a convex or a concave mirror, which we generally present as a curved surface. Just zoom in close enough until that curve basically resembles a straight line. And then you can kind of guess or estimate how that mirror will work. Okay. Pretty cool, huh? Now, when we're dealing with mirrors in particular, we will go ahead and deal with basically spherical mirrors. There are two properties that are particularly helpful when dealing with the focusing elements. One of them is the focal length. So the distance from the center of the mirror to the point where all of the light rays converge. Okay, so that will be helpful. It turns out that the focal length can be used to determine where the image will be formed. So number one. The second one, when we're dealing with these mirrors, we will go ahead and, although parabolic mirrors are by far better at focusing, we will, as a first approximation, deal with spherical mirrors, and therefore the location of the center of curvature is an important feature that will help us deal with these systems. Okay? So why don't I go ahead, now that we have an idea about concave and convex mirrors, why don't I go ahead and give you an idea about how we qualitatively analyze a mirror, and then once we have that, we can start thinking about how to do multiple mirrors sequentially. So this part is called a ray diagram, and as I've already said, it is a qualitative assessment of the focusing elements. Now, some notational issues. I've already started using this to a degree, but the idea is that when we draw a solid arrow on a ray diagram, that represents the ray of light. And then dashed lines, so the ray, the way that the ray is actually going. So imagine it comes off a mirror. You could think of these as being indicative of the direction that the actual light is going. When appropriate, we will also have dashed lines, and dashed lines represent the projection backwards of the reflected ray. So, for example, I have an incoming ray coming from the left. It gets reflected going straight up. And if I want to indicate from where the reflected ray appears to originate, you could do that by drawing a dashed line backwards. So if I were actually sitting here at the top of the page observing that reflected ray, and if I knew nothing about the mirror whatsoever, it would appear to me as though the reflected ray came from this location in space rather than, say, over here. So that's how we do that, is dashed lines reflect from where the reflected ray appeared to originate. Sometimes that's helpful, sometimes it's not. Okay? So it just depends situationally, and we'll see when that happens. Now for a ray diagram, there's a couple of things that we need to draw. Number one, I always encourage you to draw in some line to represent the optical axis. And for purposes of this class, we will assume that we have some sort of rotational symmetry. So if I draw a mirror, a concave mirror, you can pretend that that's rotated around the optical axis to form the actual mirror. Okay. Now, objects and resultant images are also drawn as arrows. After you have your optical axis drawn in, generally the tradition is to draw the object represented as an arrow with the tail of the arrow touching the optical axis. Now this is done simply because because we need some way of telling if the object is standing up, right side up, or upside down. So the direction that the object or the image is going to be oriented is indicative of the direction the arrow is pointing. Okay. Now, we will find out that if we have an object, there should be a second arrow somewhere on the screen that represents the image. Sometimes the image is going to be smaller, sometimes it'll be larger. Okay? Sometimes it'll be right side up, sometimes it will be inverted. And the ray diagram will give us some basic ideas about that. Okay. Oops! Oh no, now I went too overzealous there. Okay. Now how we're going to actually find this. And how we're going to find this out are using 3 primary rays or principal rays. Now, these, I wish I could give you a better sense of how to memorize these or how to kind of keep on these. It's not that these are the only 3 rays of light that are being produced by the object or reflecting off the object. Okay? These are simply the 3 most useful rays of light that come from the object. So of course, if you're talking about Greg, right, there's a ton of rays of light coming in, bouncing off Greg, going to the camera. Okay? The thing, you don't care about all of those rays, you only care about the 3 primary ones. The first one is the one that is parallel to the optical axis. And this ray, when it strikes the mirror, will be directed towards the focus. We saw that already, that we want to construct our mirror so that rays parallel to the optical axis go through the focus. Now, for sake of argument, I'll go ahead and say that the focus is right here. Okay? So the first ray that we're talking about, let me do it in some different color. We'll do it in orange. The first ray we draw coming from the top of the object, parallel to the axis, optical axis, striking the mirror, and then for sake of argument, we'll say that this is the focal distance. And so, striking the mirror, it will reflect off and pass through the focus. So there is our first primary ray. Our second ray will be the one that goes from the top of the object and strikes the mirror exactly on the optical axis. And in fact, you already know what should happen. What's the orientation of that tiny segment of the mirror that's on the optical axis? Yeah, good. It's perfectly vertical. So if we zoomed in right there on that piece, we would see that the mirror is perfectly vertical, just that tiny segment. And so when this next ray strikes the center of the mirror, good, it'll be reflected off at the same angle, and it will keep going. Okay. Do that. And notice that the incidence angle is the same as the reflected angle. So that's the second helpful piece. The third one, which is slightly harder to see, is that there's also a curvature, a center of curvature for this mirror. Now, I haven't drawn anything in. Again, let's go ahead and we'll arbitrarily pick a location. Let's say that this curvature of the mirror is right here, the center of curvature. This third primary ray will go from the top of the object. It will go through the center of curvature and strike the mirror. Okay. I have not drawn a very good mirror here. Okay, let's just be clear on that. In fact, I'm going to get rid of these other 2. Okay. So here's the focal distance. This one is the center of curvature. Okay. Now, when that ray passes from the top through the center of curvature and strikes the mirror, okay, what's the orientation of the little piece of the mirror that ray will hit? You say, well, it's going to be angled and yada, yada, yada. Let me ask you a different question. How does the normal, the direction of normal for that little piece of mirror compared to the direction that the incoming ray is traveling along. And the key is that ray passes through the center of curvature. Because that ray passes through the center of the curvature, the ray coming in will be parallel to the normal of that little piece of the mirror. In other words, the ray will be reflected back along the same path. Okay? And that is really important. So the ray that passes through, I shouldn't say along the radius of curvature, I say through. Well, along the radius of curvature is fine. Okay? That ray will be reflected directly backwards. Okay? Well, let's go ahead and get some practice. And first of all, notice this is going to be a drawing thing. Okay? You need to be at least fairly careful with your scaling. Okay? So that's the first thing. When you draw these out, now you don't have to, if you have graph paper available, I highly encourage you to use it. But if you're drawing this out by hand, you don't have to get it down to the minute detail, but you do have to be fairly careful. Well, let's go ahead. Let's go ahead and consider the case of a spherical mirror. So I will be slightly more careful here. Let's go ahead. I'll draw an optical axis. I'll put my my mirror here, and let's pretend that this distance represents the focal length. And I'll say that, like I had in the previous example, or like I gave as a suggestion, I'll assume the curvature is twice as far away as the focal length. Okay? And for kicks, let's go ahead. I'm going to put an object. I'll put our object is somewhere between the focal length and the center of curvature. Okay. Good? Now, let's go ahead and draw in the three principal rays in order to get a rough idea, where is the image going to be located? Is it going to be magnified or demagnified? So is the image going to be larger or smaller? And lastly, is it going to be right side up or upside down? So those three things. Where is the image going to be located? Is it going to be magnified, demagnified? And is it going to be right side up or upside down? Go ahead, take a minute, hack it out. Got it? Yeah, good. So let's go ahead. First one I said is let's draw the ray parallel to the optical axis. So ray parallel to the optical axis. Okay. And then what will happen? It strikes the mirror and it should pass through the focal point. So it passes through the focal point right here and it continues on. So this is the path that a ray from the top of the object striking the mirror and keeps going. Good? Second one. The second one, we said, okay, let's take a ray. I'll do this one in green. We'll take a ray from the top of the object. It's going to strike the center of that mirror and reflect off at the same angle. So we'll see if I can do this at least somewhat reasonably well. So it reflects off at roughly the same angle. That's not quite high enough. Nope. Okay, I'll buy that. Okay. So immediately you can see that the image is going to be magnified. You can see that I started off with an object right side up and small, and where these two rays happen to converge, I get a larger object that's upside down. So right away we can say it's going to be magnified and inverted. But we should make sure that we have that. Okay. So incidentally, you can always find a location in space where two lines will cross, right? Intersect. Okay. We want three. Three is like the nail in the coffin. If you get two crossing, well, so what? But if you get three crossing at the same location, then you're good. Okay. And now you can see my scaling's not quite right, but we'll take it. So the third one, you notice, okay, well, here's the center. You could imagine that ray going from the center, it passes just over the top, and I come up right here, and I reflect off the mirror, and it should come backwards through that center. Okay, well, I'm cheating a little bit, but through that center and passing right here. Okay. So those three rays emanate from the top of my object. The intersection of those three should be the top of my image. Cool, huh? Of course, if you'd prefer a more, complete diagram, here you go. Okay. So, the next question, okay, well, we should ask ourselves, this is always a good one, okay? If I think about these three lines, okay, this is kind of a what if. We could see this, but what if, okay? Let's pretend for a second that I take my object and I shift it even closer to the mirror. Okay? And the question is, what really happens? It's always good to think about, well, okay, now I got an idea, but what happens if I change something? Okay? And you can sort of get a sense of what happens. Now, first of all, let's focus in on the red ray. Okay? Does the red ray change at all? You say, no, of course not, right? Like, it doesn't matter if I draw the object here, if I draw it here, or if I draw it here. The red ray represents the line parallel to the optical axis. It reflects, it goes off the focal point. Okay? So that red ray won't change regardless of where I place my object. Okay? What about the green ray? What happens to the green ray as I move the object, say, closer? You say, okay, that green ray, rather than being at some, modest angle, as the object moves closer, you can imagine that green ray will get more and more extreme, right? It'll get the angle that the ray makes with the normal will get larger. So what does that mean? That means that as the object gets closer to the focal point, this green ray will sweep farther and farther down. Right? It'll go further down. Which means you can already get an idea what happens. The red ray stays the same, but now that green ray is going to sweep further and further down, right? Oh, excuse me. Oh, wow. Will sweep further and further down. And so this intersection point between the red, the green, and presumably the blue ray, that intersection point, will it get closer to the mirror or will it get further away? Yeah, good. It'll get further away. Okay. So as the object gets closer and closer to the focal point, the image will get larger and larger in magnification. Okay. Now you say, well, wait, what about the blue ray? The same thing. As the object moves closer to the focal point, you notice that the angle of the blue ray, or maybe I should say dark purple, will get less and less steep, right? In fact, I can draw a second one in real fast. It'll come in, come back off, reflect off, go through the center, and you see that it gets less and less steep. And so the same thing will happen. That intersection of the blue ray with the red and the green ones will happen further away from the mirror. Cool, huh? Okay, let's just check in. You could say, is there a limit? I go, yes. We said that the blue ray will get less and less steep. The green ray will get steeper and steeper, and the red ray won't change at all. Okay? And you can imagine what would happen. Is there a point where the blue line, the reflected red line, and the reflected green line end up being parallel? Right? If the blue line gets less and less steep, eventually it will be parallel to the red line. If the green line gets more and more steep, there is a point at which it'll eventually be parallel to the red line. And we interpret that as meaning that that is the location where an image is formed infinitely far away from the mirror. Those lines, those rays, do not intersect, or maybe a different way to think about it is they intersect at infinity. The location of the object when that happens, you guessed it, it's at the focal point. If I place the object here and I do everything correctly, it turns out that the blue ray that passes through the center, oops, I'm missing, the green ray, let me change it, get rid of those because we don't need those anymore. The green ray will reflect off, oops, don't need that, will reflect off and come out, and these three rays will be parallel to each other. Go ahead, try it out. You're probably familiar with this. If you take a spoon, this is mine. I didn't steal it from the CC, okay? But if you take a spoon and you look at the image in the spoon, you'll notice, if it's shiny, that the image is upside down, right? But if you move your eyes closer and closer and closer, well, first of all, I have to close one eye because I can't keep both of them open. It's too close. But if you keep one eye open, you can see the image, But as you move it closer and closer to your face, first of all, the image gets larger and larger. That should make some sense. You're moving closer to the focal point of this mirror. But the second thing is you get to a point where you can't form an image anymore. Right then, when your eye can't form an image anymore, it's because your eye is essentially at the focal point. There is no image being formed, or maybe... Well, let's go the other way. How about a convex spherical mirror? So concave is like a C. Convex, so I'll draw my optical axis again. Convex is the opposite way. Now, I don't know why I always struggle with concave and convex. I wish I could tell you why and, what some reason for it, but the answer is it's like adding 5 and 7, like just something that I always struggle with just a little bit. Okay, so first off, one of the things that you notice, compared to last time I had the radius of curvature on the left side of the lens because the lens was curved that way. So the first thing that we have to recognize is that both the focal point and the radius of curvature will be on the right-hand side of the mirror. So you can think of the mirrored surface as here on the left, but the focal point, F, and the radius of curvature are both on the right-hand side. Now let's go ahead. I'll go ahead and put an object here. And take a minute, pause the video, go through and draw your 3 primary rays. Got it? Yeah, good. Good. So first off, we go, okay, well, first ray. Now here we have to be a little bit careful because you know that it's a reflective surface. And how will this ray work? It's not going to be reflected towards the focal point. Right? It's not like it's going to be reflected this way because that requires it to pass through. What I will say is that it will be reflected directly away from the focal point. In other words, the reflected ray will seem to have emanated from this location in space. So how we do that, again, that's where the dashed lines come in. And then I can draw it this way. So it will have seemed, if you knew nothing about the mirror, it will have seemed that the ray came from that location in space. Okay. Let's go for the second one. I think just to be consistent, I'll do it in green. Green one is the one that we will have it intersect the optical axis and it will reflect with the same angle. That seems a little big. Try that one more time. Okay, we'll call that good. And immediately, using these 2 rays, you can say that the red and the green ray, there's no way that they'll intersect on the left-hand side. Okay? Number one. Okay? Second thing is, we need to look at the projection of that reflected ray. And so we're thinking about that piece. And so I will, again, use dashed lines to represent the location in space from which that reflected ray appeared to emanate. And thirdly, the last one is we better draw the ray from the tip of my object towards the center. So again, that one comes in, we're going towards the center, and right here, it will reflect normal to the surface, and so it'll be reflected backwards that way. And again, you can see if I knew nothing about the mirror, that reflected ray will have appeared to have emanated along that purple dashed line. And so although we see that the primary rays do not intersect in space on the left-hand side, they do appear to have originated from a common origin right here. So please bear in mind, okay, first of all, the light rays actually don't intersect. The physical rays do not actually intersect. But because of how they're spreading out, there seems to be a common point from where they all appear to have emanated from. Okay? And so it is that location where the image is formed. So if you are standing over here, looking at this mirror, what you would end up seeing is an image where it is right side up, it is demagnified, it is smaller than the original, okay, and a third piece here, okay, so it's right side up, it's demagnified, and the third piece, this is a new terminology, we call this a virtual image. That last point comes in because the actual rays never intersect. Okay? They only appear to have intersected from someplace else. They seem to have emanated from a common origin. A different way to think about it is if you have to use dashed lines to form your image, then it is virtual. Some other books will say, hey, wait a minute, if I were to actually place my eyeball right here at this location in space, I wouldn't actually see any light rays, right? And that should make some sense. The light rays came from the left side of the mirror, they bounce off the mirror and they go flying out onto the left side of the mirror. So if I were to actually put, say, film here or an eyeball or something, I wouldn't actually see the light rays. Standing on the left-hand side, again, it's where the rays appear to have originated from. As it turns out, and you can convince yourself of this, okay, for convex mirrors, okay, for a convex spherical mirror, you always end up with a demagnified right-side-up virtual image. Okay. Now, check me on that, but strictly, I believe that's correct. In fact, we can see it. If I move my object closer to the mirror, the red line stays in the same location. Okay? The blue line gets a steeper and steeper angle. Well, they'll never intersect on the left-hand side. What will happen is they'll only intersect on the right-hand side. Okay? That steeper angle. And similarly, the green line will get a steeper and steeper angle so that the projection, again, is on the left-hand or the right-hand side of the mirror. Okay? For those of you that want a better diagram, okay, there you go. So that one, that one has been drawn to scale. You go down to the Circle K, look to see if you see those mirrors in the corners of the grocery store. Okay, what they do is they allow you. Some people say, "Oh yeah, they allow you a larger field of view." That is, vernacular for saying that it demagnifies. Right? It's not a true one-to-one. It allows you to see more of the store because it's producing a smaller image. So that's the place where I always remember seeing them. So, any case, I think that's probably enough information for this go round. So keep up the good work, bring questions to class, and I'll see you next time.